In this lesson, we're going to discuss hashing. Now, in network security, integrity is usually provided through the use of a hashing function. Hashing is a one-way cryptographic function that takes an input and produces a unique message digest as its output. Because this function is one way, there is no way to determine the original message based on the message hash or hash digest that's being outputted by this algorithm. The resulting message digest will then act like a digital fingerprint for the original file. Another unique thing about a hash digest is that they're always going to be the same length, regardless of how long your input is. Whether I input a file containing 1 word or a file containing 1 million words, the output will always be the same length based on the hashing algorithm you chose. Now, when it comes to hashing, there are a few main algorithms that you need to be aware of, including MD5, the SHA family, RIPE-MD, and HMAC. First, we have MD5, which is by far the most popular and widely used hashing algorithm over the past few decades. Now, the MD5 algorithm is going to create a 128-bit hash value that is unique to the input file. Unfortunately, because the hash value being output is only 128 bits long, it can only create a limited number of unique values, and this can lead to two files having the exact same resulting hash digest, which we call a collision. Now, due to the limited number of unique hash values associated with MD5, a newer family of algorithms was created called the Secure Hash Algorithm family, or SHA. Now, the SHA family, or SHA, includes SHA-1, SHA-2, and SHA-3, which are all families of hashing algorithms. Now, SHA-1, for example, creates a 160-bit hash digest, which significantly reduces the number of collisions that can occur over MD5, since MD5 only had 128 bits instead. SHA-2 is a family of hash functions that contains longer hash digests. This includes SHA-224, SHA-256, SHA-348, and SHA-512 hashing functions, and each of those has a digest between 224 bits up to 512 bits, as their name suggests. Now, each version of SHA is going to perform a different number of rounds of mathematical computations to create their hash digest, anywhere from 64 to 80 rounds, but you really don't need to know the specific number of rounds for each version of SHA. Now, SHA-3 is a newer family of hash functions, and its hash digest can go between 224 bits and 512 bits, just like SHA-2 could. Now, the biggest thing here, though, with SHA-3 is that it has a major increase in security because it uses 120 rounds of computations to create its message digest for each unique file instead of the 64 to 80 rounds used by SHA-2. Now, the third algorithm we have to talk about is the RIPE-MD hashing algorithm. Now, RIPE-MD stands for the Race Integrity Primitive Evaluation Message Digest, or RIPE-MD, and it comes in 160-bit, 256-bit, and 320-bit versions. Now, with the 160-bit version, this is going to be the one that is most commonly used, and you'll hear people talking about this as RIPE-MD-160. Now, RIPE-MD-160 is considered to be an open-source hashing algorithm that was created as a competitor to the SHA family of hashes, but it really hasn't gained the same level of popularity that the SHA family has. Now, the fourth and final one we need to talk about is HMAC. HMAC is the Hash-Based Message Authentication Code, or HMAC. Now, HMAC is used to check the integrity of a message and provide some level of assurance that its authenticity is real. Now, HMAC will actually be paired with other algorithms to do the work, and so it'll be called something like HMAC-MD5, or HMAC-SHA-1, or HMAC-SHA-256, depending on the underlying hash that's going to be used with HMAC. Now, one of the most common applications of hashes is for us to create a digital signature to ensure the integrity of a file or message as it's being transferred over our network. A digital signature is created by hashing a file and then taking the resulting hash digest and encrypting it using a private key. So if I want to send an email that's going to be a couple of pages in length, and I want to digitally sign it to make sure you know that nothing was changed inside of that email, I can run that email message through a hashing algorithm like SHA-1, and then take the resulting 160-bit hash digest from the SHA-1 algorithm, and then I can encrypt that using my private key. When I send the email over to you, I'm going to attach the resulting encrypted hash, which we call the digital signature, along with the message, and then this is going to prove the integrity of the message, and it creates non-repudiation. When your system receives my email, it's going to decrypt the digital signature using my public key, which is going to provide you with that original 160-bit hash digest. Now, your system takes that multiple-page email and runs it through its own version of the SHA-1 algorithm. Then it compares your message digest that you calculated with the one I sent as part of my digital signature. If those two things match, then you can be assured that the email was not modified in transit between my system and yours, and this provides you with the integrity check. Now, since I also encrypted that SHA-1 digest with my private key, and only I have my private key, This also assures you that the person who sent the message is the only person who could have sent that message, and this provides you with non-repudiation for that email. This non-repudiation means I can't claim that I didn't send the email to you because I'm the only one who could have, because I'm the only person in the world who has a copy of my private key. Now, to practically use digital signatures, you need to use an algorithm for that, and we're going to either use the digital security algorithm, known as DSA, the Rivest-Sherman-Alderman cipher, or RSA, or the elliptic cryptography version of either DSA or SHA. Now, the federal government has decided to use the digital security standard, which they call DSS, and this relies upon a 160-bit message digest created by the digital security algorithm. Now, most commercial entities, though, will rely on RSA instead because it tends to be faster and can be used for digital signatures, encryption, and key distribution. Digital signatures have also expanded beyond just emails, too. Code signing over files relies upon the digital signature for a program or file being added to that file. For example, if I create a new mobile application and I want to put it into an app store like Google Play or the Apple App Store, the installer file will have to be digitally signed, and this is what we refer to as code signing. Now, every developer must register with Apple or Google, and they'll receive their own private key. Just as the email example I provided earlier, the application file will be hashed, and then that hash will be encrypted using the developer's private key. This is what we call code signing, and it ensures the installer hasn't been modified or corrupted since the developer actually published it. Now, I know we covered a lot here already, but before we close out this lesson, I want to provide you with a quick demonstration of how drastically the hash digest will change if the source text or file is changed even a little bit. To do this, I'm going to use an online MD5 hash digest generator to create two slightly different inputs that will result in a very large difference in their outputs. On the left, I have an online MD5 hash generator, and on the right, I have a text file of the US Constitution. Now, what I'm going to do is I'm going to copy this entire file of the text file of the US Constitution and place it into the box. And immediately, what is going to end up happening, if I go up to the top, I have the entire text here, and we have this hash string down here at the bottom. Now, the hash string at the bottom is unique to that Constitution and the word and the order that those are in. If I change even one letter in the Constitution, that hash is going to be drastically changed. And I'm going to demonstrate that to you right now. So if I go here, there's the word defense with a CE, which is the British spelling. But as Americans, we don't spell it that way anymore. We spell it as DEFENSE. So if I change the C to an S, watch that hash value as it changes. I'm going to do that in 3, 2, 1, change. Notice a vast difference in that hash. That's why one letter makes all the difference when you're dealing with hashes. Because of the way that these are computed, they come in one way and they come out a different way, and they come out the same way every time based on what's input. So let me show you another example of this. Let's go ahead and say I have the line 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. And I'm going to treat each line as a separate hash now. If I went and said, let's do it as 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. They're vastly different because I shifted the position. You'd probably expect that. But what if I did 1, 2, 3, 4, 5, 6, 7, 8, 9, 0? They're both the same now, and I added a dot. Well, that's going to change the bottom one drastically. If I go back, it's the same. If I add a space, it changes it again. Every time you add any differences, whether it's one bit or one character, it's going to drastically change that MD5 output. And that's why MD5s are considered a way to verify integrity. It verifies that the original input was never changed in transit because the hashes match. There could be no changes. Now, are there any cases where two different things will give you the same hash? Yes, this is called a collision. They do occur. Because an MD5 only uses 128 bits to represent that hash value, that is going to give us a limited number of choices, but there are unlimited number of inputs. So when you have two that give you the same hash value, that is called a collision, and that is a bad thing. So because MD5 only has 128 bits, it does have more collisions than something like SHA-1 or SHA-256 or SHA-512, because as you extend that space of what that unique hash value can be, you have less collisions. And that's why most people have moved to SHA-1, SHA-256, or SHA-512 as we've moved forward into the future. So remember, hashing is a one-way cryptographic function that takes an input and produces a unique message digest as its output. Because this function is one-way, there is no way to determine the original message based on the message hash digest. Because this function is considered to be a one-way algorithm, there is no way to undo it and then determine the original message based solely on the message hash or hash digest that you received as an output from that algorithm. This makes the hash digest or resulting message digest act like a digital fingerprint for our original files that we're sending around. There are also a few commonly used hashing algorithms that you need to be aware of, including MD5, the SHA family, RIPE-MD, and HMAC. The most secure of these is going to be the SHA family of algorithms, and specifically SHA-256 or SHA-3. Finally, remember that digital signatures are basically just an encrypted hash digest that's going to be attached to a given file. This digital signature is created by hashing a file and then taking the resulting hash digest and encrypting it with the signer's private key.